So each element consists of unique atoms, and an atom is the smallest unit of matter that still retains the properties of an element. Atoms are composed of even smaller parts called subatomic particles, and in some cases, those subatomic particles are composed of even smaller parts called quarks, which we won't really get into. You are expected to know that the nucleus is made up of protons and neutrons. Protons are positively charged, neutrons are neutral, and they collectively determine the atomic mass. If you alter the number of protons in an atom, you will change the identity of the atom. If you alter the number of neutrons in the atoms, you will make an isotope. So we can see, for example, that helium here, the protons plus the neutrons, which determines the atomic mass, the average atomic mass for helium is 4.003. That tells me that most helium atoms are 2 protons and 2 neutrons, but there are definitely some with more neutrons. Outside of the nucleus, you have the electrons. The electrons are going to be forming that negative cloud on the outside. They're going to be the major thing that determines chemical behavior, like noble gases not really interacting with things come because of the full electrons in the outer valence shell, but you should get the general idea. So if you alter the number of electrons, you will make an ion. If you have a negatively charged molecule, you have an anion, A-N-I-O-N. If you have a positively charged molecule, you will have a cation, C-A-T-I-O-N. So the atomic number is important because the number of protons will help you identify the atom. The atomic mass is the average of the isotopes. The charge number will tell you the balance between electrons and protons, but you should have a basic idea for how the atom works. About 20 to 25% of the 92 naturally occurring elements are essential elements. That means that they're necessary for living things. There is, of course, some variation. Humans have 25 essential elements, while plants only have 17, but the overall balance is roughly the same. 4 elements, oxygen, carbon, hydrogen, and nitrogen, make up 96% of living matter. Most of the remaining 4% of an organism's weight consists of things like calcium and phosphorus and potassium and sulfur, and there are trace elements that are required but only in minute quantities. That might be something like iodine, copper, okay? You get the general idea. Vertebrates, okay, we require iodine for normal activity of the thyroid gland, and if you don't get iodine, you're going to have a disease called goiter. So we get the basic idea that these elements, these atomic components, are necessary base components for life, and that's something that we need to be aware of. So organisms are composed of matter, which are defined as anything that takes up space and has mass. That matter is made up of elements, and elements are substances that cannot be broken down into other substances by chemical reactions. We should have that basic idea. Compounds are going to be substances that consist of 2 or more elements in a fixed ratio. That might be something like table salt that we're looking at here, which is sodium chloride. Although pure sodium is a metal that's kind of explosive in water, and chlorine is a gas that is toxic and poisonous, they combine to form an edible compound. How do they do that? That's where bonding come in. So when bonding happens, when 2 elements interact during a chemical reaction, it's their electrons that are involved. The nuclei don't come close enough to interact. We're not looking at nuclear reactions right now. The electrons vary in the amount of energy they possess, so you have that potential energy difference. So you're going to have these electron shells. They're kind of more of a fake image than anything else looking at orbitals. They're not really real, but they are useful for figuring out these broader relationships. On that first shell here, you can see that there are 2 electrons that fill it up. For all of the later ones, there are 8 valence electrons. So atoms are going to be trying to balance their electrons so that the outer shell is going to have full valency. They do that through different types of bonding. So sodium, if you see here, only has 1 electron in its outer shell, making it very reactive, which is one reason why it explodes. Whereas chlorine has 7, it only needs 1. So sodium can give that electron to chlorine as part of an ionic bond, and that will then be stable for both, creating something that's non-toxic. The chemical behavior of an atom is determined by its electron configuration, the distribution of electrons in those outer shells, and those are balanced through different types of bonding. Like we said, the interactions that are resulting between these atoms, they are looking at what's holding them together, the attractions between them, and we refer to those as chemical bonds. The strongest chemical bonds are covalent bonds and ionic bonds. A covalent bond is going to be formed when two atoms share a pair of valence electrons. What determines if it's going to be shared, though, is the electronegativity of the bond. So strongly electronegative atoms are going to strongly pull on the electrons. So if you have a covalent bond that the pull in either direction is equal, then you will have a nonpolar covalent bond. If the pull is unequal, you will have a polar covalent bond. If the pull is so unequal that the valence electron is essentially stripped, it spends all of its time around the other atom, that is an ionic bond, and you'll make a cation and an anion every single time. So if you know the electronegativity of the atom that you were looking at, it's really down to the degree of difference. If there is very little difference between the electronegativity, then it will be nonpolar. If there is a lot of difference, then it will be polar. You should roughly remember that electronegativity increases as you go up and to the right on the periodic table, and that will make more sense when you look at different types of bonding, like hydrogen bonding. Within a cell, weak, brief bonds between molecules are important to a variety of processes. In biology, we don't really care about ionic bonds because ionic bonds break in water, and we are aqueous organisms, so they really don't matter. But we have a lot of water, and water is a polar covalent molecule. Because it is polar covalent, it can create weak charge differentials, kind of like a magnet passing back and forth, and that attractive force is what we call a hydrogen bond. Since the hydrogen has very little hold on its electron and oxygen has a very high hold on the electron spends very little time around the hydrogen. So hydrogen becomes partially positive, the oxygen becomes partially negative, and that creates that hydrogen bond. It's like a magnet. Okay. This is part of a broader sort of thing looking at what's called van der Waals interactions. Although individual bonds like ionic and hydrogen and van der Waals are temporary and individually weak, they are collectively strong and play an important biological role. Now, water is not the only thing that's capable of hydrogen bonding. You really just need something that has hydrogens attached and has a really high electronegativity. So nitrogen, oxygen, fluorine, and chlorine are all technically strong enough to create hydrogen bonding potential. We will be disregarding chlorine even though it has the same level as nitrogen because chlorine is so heavy it doesn't really work within aqueous situations. So for the most part in biology we can ignore chlorine, but if you're taking AP chemistry you can't ignore chlorine. So you can see the example here, ammonia with nitrogen instead of oxygen can also create a hydrogen bond. Why do we care so much about those hydrogen bonds? Well, hydrogen bonds give water those properties that make water essential to life. Water is a polar molecule. The opposite ends have opposite charges, and the hydrogen bonding gives water a variety of unusual properties. The slightly negative region of one water molecule being attracted to the slightly positive region of another forms those hydrogen bonds. Each water molecule can form hydrogen bonds with as many as 4 neighbors. And when water is in its liquid form, that hydrogen bond is very, very fragile. So they break and reform with great frequency. They may only last a few trillionth of a second, but you're forming so many of them that it's collectively strong. So because of that hydrogen bonding, some of the properties of water are its density. Ice is less dense than liquid water. It is the only substance that we are aware of that the solid form is less dense than the liquid form. And that's really useful. It means ice floats, insulation, when water freezes, then the potential for life surviving is very useful looking at things like snowball Earth and other situations. Surface tension, capillary action, the meniscus within a graduated cylinder, all of these are components of that structure that are looking at what's going to be going on within organisms. So that'll make more sense as we go forward. Adhesion and cohesion. Adhesion is when water sticks to other things. Cohesion is when water sticks to other water, and that's going to be useful looking at components like evapotranspiration, which we'll look at in a moment. Water is a very good solvent. The thing, oh, it's a universal solvent. That means that water would dissolve everything. Of course, that's not true. Water is a very good solvent for polar things. Water is polar, like dissolves like, so water is good at breaking down other polar things. But that's also why water doesn't break down something like oil, for example, because oil is non-polar, like dissolves like. And then we have specific heat. So because hydrogen bonds are very fragile, they can absorb energy. Okay, that means that things like evaporative cooling and climate and that kind of thing, water resists changes in state. So water is able to absorb a great deal of energy and control that reaction. So we here in South Carolina, we have very even nighttime temperatures and daytime temperatures because we have so much water. But if you were to go somewhere like Death Valley, night is going to be incredibly cold because there's very little water to moderate that climate. And it's the same reason why evaporating sweat cools you down, because the evaporative sweat, the heat is being absorbed and breaking the hydrogen bonds and turning the liquid water into gaseous water. Out of these ideas of the properties of water comes the idea of water potential. Water potential is defined by its chemical activity, and water that has the potential to move or has a higher amount of energy is going to be able to flow through these systems. This is going to depend upon components like solute concentration and all these kind of things, and it's one reason why water is so important to plants. Potential in water potential refers to the water's potential energy, its capacity to perform work. Collectively, water potential drives this process called evapotranspiration. Transpiration provides the pull for the ascent of sap in plants through the xylem. The cohesion of water molecules transmits the upward pull along the entire length of the xylem. You have evaporation happening at the stomata, and that's going to be driving the plant structure. We're going to look at this mathematically when we get into cells, but the properties of water like adhesion, cohesion, specific heat, all of those components come together to drive these broader biological processes. One thing we'll get with as we get into transpiration as we go through later components, transpiration, T, is tact. Okay, transpiration is a combination of adhesion, cohesion, and tension, surface tension. So surface tension at the stoma or at the surface, that's going to be evaporating away. Then you're going to have adhesion and cohesion, the water sticking to water and water sticking to other things, pulling it up like a great big straw with the suction power coming from evaporation at the leaf. Plants don't have a heart or a pump to pull these through, so this evapotranspiration drives a lot of the plant's biological processes. So occasionally a hydrogen atom is going to participate in a hydrogen bond between two water molecules and will shift from one molecule to another. Okay, the hydrogen leaves its electron behind and is transferred as a single proton or a hydrogen atom, which we represent as H+, a hydrogen ion. Okay, the water molecule that lost the proton is now a hydroxide, and the water molecule that gained the proton is hydronium. So that's really what our pH system is based on. It's based upon water and the movement of hydrogen. So we use a pH scale of 14 because that's what water does. But pH is equal to the negative log of H+. Okay, that's going to be a base formula that you should be able to do. Okay, as things become more high in the concentration of protons, that's going to be made it more acidic. So any substance that increases the hydrogen ion concentration is an acid. Any substance that reduces the hydrogen ion concentration is a base. Okay, you can have strong acids and weak acids and whatever. Okay, we get the general idea. The pH decreases as the H+ concentration increases. Now this is a log scale, so that means that battery acid is 10 times more acidic than gastric juices, okay, 100 times more acidic than soda, okay, and 1,000 times more acidic than tomato juice. You get the general idea. So as the pH goes towards 0, you're going more acidic. As the pH goes towards 14, you're going more basic or alkaline. Now, when you're actually trying to calculate these things, it can get pretty confusing. You're looking at concentrations of very, very tiny amounts of molecules. But if we remember that this is a negative log, then that becomes pretty easy. Okay, so if you turn this into scientific notation, well, 1, 2, 3, 4, 5, 6, 7, that's 1 times 10 to the negative 7th. Okay, that means that the pH is 7. Okay, 1, 2, 3, 4, the pH is 4. Now this one is a bit of a flip. This is looking at the OH. Okay, well, 1, 2, 3, 4, 5, 6. Well, our pOH is 6. Water scale is based on 14. So if 14 minus 6, that's equal to 8. Our pH is 8, and our pOH is 6. So long as you are looking at an aqueous organism, you can use this trick, this 14 idea. But if you're looking at something outside of that, you can't. So in chemistry, use your calculator, negative log of H+. In biology, you can move it along. Now, what if the number's not 1? Go to your calculator. It's not worth the effort.